Hello, my name is Ken Drysdale. I'm the CEO of the Theodoma Group. Welcome to Rudley Home, the dwelling of Mr. and Mrs. James Conwell. In the shed behind me is a test rig which demonstrates that Theodoma has developed a cooling system with a COP of between 15 and 30. As you know, COPs in excess of 10 have never been created before outside laboratory. This is a truly significant sea change in the whole of the refrigeration industry worldwide, and we are proud to announce this result. I'm now going to ask you to come and have a look at the equipment and to have a look at the data logging and the data we're producing, and to eventually build up a picture for you so that you can see that the COP that we are claiming is in fact authentic and based on data acquired over a number of days. Is a PlantWatch Pro automatic data logger. It is logging the key temperatures around the thermodynamic cycle in two groups, labeled Temp 1 and Temp 2. There are 4 temperatures in each group, and you can see from the screen that the first temperature here is the condenser output, which is at 33.5 degrees centigrade. The water tank is used for subcooling and is at 13.6 degrees, and the ejector nozzles are driven by high-grade refrigerant vapor at 54.1 degrees centigrade. The receiver temperature is 24.4 degrees C. The evaporator output is 51.1 degrees centigrade, and the condenser input is 53. The receiver is at 24.4, which is the beginning of the cycle, and the evaporator, which is actually absorbing the heat from the ground, is at 51 degrees centigrade. What that means is that the vapor is exiting the evaporator at 51.1 degrees. In a minute, we'll be able to see, when we change the screen, the evaporator input temperature is at 26 degrees. So very similar to the condenser, there is something of the order of about 24 degrees difference between the evaporator input and its output. The evaporator input temperature is 27.6 degrees. This means that the vapor is going through the complete ground matrix of about 300 meters of copper tubing, broken up into groups of 5, making an individual run of about 75 meters. On transition through the 75-meter run, the evaporator temperature is rising to 51 degrees. The preheat output, which is the coil that actually supplies preheat to the ejector input, is at 25.7 degrees. As can be seen, there is a considerable amount of ground heat being collected with sub-zero temperatures outside, where you can see snow and frost. So a system like this can work not only in hot climates but also in cold. What can be seen in this view is the Theodoma test equipment, which is specifically designed to prove the groundbreaking coefficient of performance, commonly abbreviated COP, of 20. The key component in the test rig is the ejector, which can be seen about halfway up to the right of the picture. The ejector replaces a compressor and is much more efficient than a normal compressor would be under similar circumstances. The equipment is much larger than would be in production. If one was to install a system in a building or a supermarket, one could imagine something which would be about half the size of what you're seeing in front of you. The instrument seen here is a Trimec flow meter, which is measuring the number of kilograms per second flowing in the thermodynamic cycle. It is absolutely essential to be able to accurately read flow in order to be able to determine the COP of the system. As can be seen, the flow meter varies from 0.4 to about 0.2. This variation is due to the cyclic nature of the thermodynamic cycle, which can be heard in background. In order to average out these differences in reading, we take the total number of kilograms measured through the system over a period of 24 hours and divide by the number of seconds, which gives us an average flow rate in kilograms a second. In this way, we average out the variations and create a far more accurate reading. The 2 meters seen in the foreground are data logging systems to log the power drawn by the pump and other parts of the system. These meters operate over a 24-hour period and log current, voltage, phase angle, and true power. It is essential to know what the true power drawn by the pump is in order to compute the COP. By using the flow meter readings seen previously, we can multiply the average flow by the change in enthalpy of the thermodynamic cycle. That gives us the total amount of heat drawn in by the system. If we then divide that by the average power taken over a period of 24 hours, we get the average COP of the system. In previous data logging runs, as mentioned before, we've been able to log values of between 15 and 26. I'd like to introduce Peter Terry, who's a member of our technical team. Peter has played a pivotal role in the construction and development of this equipment over the past 3 months. The equipment has been pumping heat into the ground for the past 5 days at a COP of approximately 20. And I'd like now Peter to go out and measure the ground temperature about 18 inches below the surface to see what the temperature has risen to. Peter, if you wouldn't mind doing that.
The ground temperature is 34.5 degrees centigrade. We're now going to look at the temperatures going into and coming out of the ground through the evaporating matrix. This is the temperature going into the ground, which is at 23 degrees centigrade. And now the temperature coming back from the evaporating matrix after it's gone through the ground. Coming back at 49.3 degrees centigrade. After we picked up the heat from the ground and put it back into the condensing matrix, we use this water tank here as a supercooler to remove any excess heat from the refrigerant to allow this process to complete. This tank was sat at ambient, which is about freezing at the present moment, and over the last 5 years has heated up with the excess heat, which is currently risen to 18.6 degrees centigrade in a 10,000 litre water tank.
By now you would have seen the Theodoma test rig producing a temperature of around 50 degrees centigrade on a cold day in the UK. This heat is extracted from the ground using the cooling engine, which has a COP, as mentioned before, of between 15 and 30. I'm now going to show you how that COP has been derived. In front of you can see a pressure enthalpy diagram. This is a plot of pressure on the vertical axis versus enthalpy on the horizontal axis. From the data logger, we've been able to produce what's called a pH diagram, which defines how the thermodynamic cycle works. And I'll just quickly run through that diagram with you. The first point 1 over here, is the starting point, where we started just below 0.4 of a bar and the pump takes the pressure up to just around about 7 bar. We evaporate along this line here from 0.2 to 0.3. And then we condense. At the beginning of the 5-day cycle, we were condensing between 0.3 and 0.4, back to 0.5, and then back to 0.1. However, as the system acquired heat, the whole of this graph was moved up. And instead of condensing between points 3 and 4, we were condensing between points 3, 4A, 4B, returning to 2. If one looks at this diagram, you can see enthalpy on the bottom here. Enthalpy is defined as the heat content per unit mass. And you can see that the cycle started at an enthalpy of around about 210 kilojoules per kilogram and finished at around about 445. If we subtract from 445 210, we get an enthalpy change of 235 kilojoules per kilogram. If we go to the formula for COP, which is merely mass flow rate multiplied by enthalpy change divided by power into the pump. The mass flow rate was measured over a long period of time, over 24 hours, as being 0.2 kilograms a second. That multiplied by 235 kilojoules per kilogram and divided by the pump input of 2 kilowatts gives us a COP, in this case, of 23.5. As was mentioned earlier on, COPs of greater than 10 have never been achieved before. Theodoma has, in fact, produced a COP which results in a sea change in the refrigeration industry worldwide. Thank you very much for your attention. Thank you.